Hey guys, welcome back to my channel. I'm sorry for the long delay for this episode. Obviously, just been kind of busy and haven't been able to keep up with it. Normally, I was filming all these videos really early in the morning, and on top of that, I just haven't been able to recently wake up as early as I was before. In any case, we're here now, and we're going to continue our work with aerodynamics and how to do straight line testing in iRacing using Motec. So let's start off with, again, this is going to be like a little bit of an advanced video because of the fact that we are going to be adding to what I already taught you in the previous lesson. So if this is your first video that you're watching, I recommend that you go back and watch episode 7 of my Motec tutorial series, Aero Balance and Drag and Downforce, because we're not going to be touching on any of that stuff and you might get lost. Okay, so this is what we're going to be doing today. We're going to take those maths that we did on episode 7 and we're going to be creating an Aero map. And this is basically the Aero map that I made for the BMW Z4. Sorry. This is the Aero map I made for the BMW Z4 GT3, and it shows front downforce, rear downforce, lift over drag. This is the aero balance. So this is the front percentage, and this is the coefficient of drag and the coefficient of lift, and this is the total downforce. So we have the coefficient of lift times the area divided by the motion ratio. And that's what we're going to be using to do our calculations, and that's how I've already entered it into Motec with the maths. Let's go ahead and look at those. So the reason why we're taking out the motion ratio is because I did spend a lot of time doing a lot of testing in between these videos trying to get a good calculation for motion ratio, and it turned out to be an absolute fail. I definitely think I tried around 8 to 10 different methods to calculate motion ratio, and the problem is that they all sound very good and they look like they give reasonable results, but then when you actually know what the correct motion ratio is for at least 2 cars, that's where the problem is. I've been able to calculate it where it's very close, or at least close enough to the true motion ratio for one car, but then when you try to do it for the second car, it doesn't work. So there's definitely a lot of issues with the calculation that still need to be resolved. So for right now, that's what we're doing. We're taking that out of the equation completely. So let's, for example, look at the downforce front. What do we see? We're going to just see these are all the gating, this part of the logic in the function that I put in. And then the actual function is the spring rate in the front times the suspension travel of the front left plus the suspension travel of the front right. And there's no motion ratio. Before, I would have had a term here that was being multiplied, that would have multiplied the spring rate by the motion ratio. So I took those out entirely, and that's what I'm using to do the calculations. Now, to do the Aero map, let's take a look at the Aero map that I already completed. To do the Aero map, you'll notice that I ended up using 4 different front right heights and 4 different rear right heights. So that means that I did a total of 16 runs. It was tedious, and I've got it down to where it's rather efficient. I can do basically 1 run every 2 minutes. It takes about 2 minutes or so to do each run, maybe 2.5. Let's round it up to 3 minutes. 3 minutes per run. So all in all, I did it in a few maybe 2 hours in total, including some other stuff that I was doing at the same time. So if you only do the testing and then you just are very efficient with your note taking, you can do it within an hour of total work. So it's actually not too bad, not as bad as it looks. It's going to require you taking some hand notes, which I did here, and you just basically sweep through the range. I had a set of combinations basically. For the BMW right now, the rules allow the front to be as low as 45 millimeters, or the total ride height. So the front or the rear can be as low as 45 millimeters, and it can be as high as 70 millimeters. So basically I have to run through combinations of the front being at 45 and the rear at 45. Then the front at 70, the rear at 70. Front 45, rear 70, front 70, rear 45. And then there were, basically I broke it up evenly. So then I also had a ride height of 53.3 millimeters and 61.66 millimeters. So those are the intermediate values. So basically between those four ride heights, I used every single combination possible, and then that totals up to 16 runs. And I'm going to show you how I did that in more detail. So just to review, you'll notice here that these are colored in yellow, and that's the one that we're going to redo, because I noticed that this value kind of just doesn't follow the trend in some cases. So I'm going to want to redo that. So that's the one that had the front at maximum of like 70 millimeters and the rear at 61.66. Now you'll notice this does not say 70. So I should, I'm going to, I guess, rename these, but these ride heights are dynamic ride height values, not the static. So basically I'm setting the car to have a static ride height of 70, but once it's on the racetrack and I'm going at constant speed while I'm doing my straight line constant speed test, the car is settling down. So the front is at 68 instead of 70, so it goes down about 2 millimeters on the average, and the rear goes down about 8 millimeters on the average, which again it demonstrates it's a function of obviously the spring rate and also the aerodynamic load on there as to how far the rear of the car squats down. But so that's the reason that these values are like that. You can do a different type of aero map where you input, and I will, because there is a purpose to having that as well. But the reason that I'm doing it this way is because I'm going to be putting these values into Motec. So then I need to have dynamic ride heights, not the static ones. So we're going to go through this, and I'm going to walk you through it. But the one that we're going to do, I'm going to redo it live for everybody, is going to be this one where the front is basically static 70 millimeters and the rear at 61.6 millimeters. And we'll redo that test, and I'll walk you through it. First, let's review what the procedure is for the test. So let's go ahead and look at the graph, because this will show one of the tests. Basically, this is me leaving the pits all the way on the left here, and I'm going to accelerate. And this is, right now we're looking at time, so it shows kind of like I'm 0, 0, 0 for several seconds while I sat there in the pits. Then I accelerate to about 60 kilometers per hour. And right now there's a little bit of a discrepancy between the display in the car and also the actual speed. So I mean, I guess it's kind of difficult, but you end up changing it. Like right now, some cars have a bigger discrepancy than others in the display that you get in your data logger that's simulated, and the little corner that actually shows you your speed. Sometimes they're different. But if, let's say, you pick 60 kilometers per hour and then you come to Motec and it tells you that you were actually going 58 or 55 or whatever, then you can just change the math so that the range is within the one that you actually were. But right now I have this. This is going to calculate your zero suspension position, which is part of the procedure. So you have to go 60 kilometers per hour for a few seconds. I guess this was like about 10 seconds worth of 60 kilometers per hour. And then that sets the suspension 0 front and suspension 0 rear. Let me show you that math. So here you see suspension 0, front left. And this is showing that it is only going to calculate, and this is going to be a mean value. So it's stat mean. So it's going to be one value that's going to stay static for the entire run once it calculates it. It's going to say, it's going to calculate off of these conditions when the speed of the car is greater than 58 kilometers per hour and less than 62 kilometers per hour. And that means that also the lateral acceleration has to be less than 0.03. So it'll cut out anything if you're not going perfectly straight. And the longitudinal acceleration, basically, if you're not holding a constant speed, it'll kick that out too. And it has to be less than 0.03. Then it'll calculate what the suspension position was and average it, and it'll lock it in. So that's how we calculate that. I have suspension zeros for the front left and front right, and then I also have it for the front altogether. So that's the average of the front left and the front right. And same thing here. Although these values here are a little bit different on this one. Again, you can play around with this and tune this. You can definitely go down to about 0.03, and that works. I come up with these values just through experimentation. So I do, I set a higher range, and then I close it down until I see that that the functions start becoming very discontinuous. 0, 3, 0, 3. So you see, that's the first step, is calculating, and you see majority of the time I was holding it between below 63, around 61 kilometers per hour. So then it calculated, had plenty of opportunity to calculate suspension 0. Then we go and speed up, and we're going, at this point at Daytona, where I did the test, I'm going through turn 1 and 2. And then I get onto the back straightaway, and I'm slowing down as I'm exiting the corner. And once we're at the back straightaway, I'm trying to hold a constant 150 kilometers per hour, and that's where we're doing our downforce test. And that one has some pretty serious gating on it, which also removes bumps out of. It has a if statement where if the vertical acceleration is too high and we go over a bump, it'll cut that information out of the calculation. So half of the back straightaway I use to hold a constant 150 kilometers per hour. And you can see this is where it calculates the front and rear downforce. So these are the moments where as you can see here, I'm showing the longitudinal, the lateral, and the vertical acceleration, and you can see that's where they're holding their most constant. And there's a little bit of a bump here, and you can see the suspension travel fluctuated, which obviously has an effect on the downforce. But for the most part, you can see the majority of these values are all very constant, and they're showing in the order of 1,400 to 3,000 newtons. So that's working. So then that calculates the downforce, which is going to go into our lift calculations, our coefficient of lift. And then about halfway down the back straightaway, then I hit the clutch and let the car coast. And it's only going to calculate drag off of the first few kilometers per hour that it loses. So you don't need to hold the clutch in the entire way. And let me show you what I'm doing with my pedals. So anyway, at this point I hit the clutch, and we have the clutch engaged, and we're coasting. And I let the car coast all the way through the turns. But it's not absolutely necessary, because there's two calculations that we're doing, that we're letting the computer perform. At the beginning, it's going to calculate the coefficient of drag. And then towards the end, when the car is going very slowly around the 20-something mile per hour range or kilometer per hour range, we're going to calculate the friction, the mechanical friction in the system. Basically, the car decelerating just because of drag that's induced through the transmission and the tires and the hysteresis in the tires and the drag through the entire system that's subtracted from the aerodynamics. So this is just the mechanical friction, no aerodynamics being involved. So where does that come in? Mechanical friction is in this regime, just in this area. This is mechanical friction, and aerodynamic drag is here. And we don't really care about the stuff in the middle, so whether or not you have the clutch perfectly in or not, it doesn't make a difference. Let's look at the math. So the coefficient of drag is calculated here. And you'll notice that I have the clutch pedal position has to be less than 7%. I played around with this. It's okay if it's as high as this. It won't actually cause any difference or in the calculation because I did it like back to back. So the math again. So clutch position has to be less than 5%. Throttle position has to be equal to 0. Brake position has to be equal to 0. Those have to be that way. And then the ground speed has to be greater than 120 and less than 150. So you have that 30 kilometer per hour range that the car is going to decelerate, and it's going to average the acceleration in between those 2 points. And then based on that acceleration, it's going to calculate what the coefficient of drag must have been, because the acceleration is obviously proportional to a force of drag that's slowing down the car. And then we have to, later we calculate or subtract out the force of friction that we calculate in the next step. So what is this? So that's the logic. To the left is the logic, and here is the actual function, and it's the car mass times the absolute value of the g-force longitudinal times gravity minus the rolling drag, which is the mechanical friction that I was talking about a second ago. And that's all divided by the dynamic pressure. So the rolling drag, so that's calculated between 150 and 120. And the rolling drag, similarly, has the same type of logic before it. And this one is being calculated between 40 and 30 kilometers per hour. Because then after that, I want to be able to hit the brakes and stop the car. But you get a pretty much the exact same. We can safely assume that at 40 kilometers per hour, there's no aerodynamic loading that's worth anything. We can count it as negligible, so then we can just perform the calculation at that speed. So then you have 10 kilometers that it averages, and then it calculates, which is just a basic equation of mass times acceleration, which is equal to force. Okay, so now we have the procedure kind of outlined for you. You leave the pits, you hold 60 kilometers per hour, then you go and accelerate through turns 1 and 2 to 150 kilometers per hour. Down the back straightaway, as you start the back straightaway, you hold a constant 150 kilometers per hour, and then halfway through the back straightaway, or where you see usually your initial braking point for the road course, you hit the clutch, let go of the throttle, and hold that clutch and let the car coast down all the way through turns 3 and 4 until you basically get to, let's say, 20 kilometers per hour. Then you hit the brakes, stop the car, exit, and then you can change the setup and then do another run. You take your notes of what setup you're running and the setup changes, and then you make sure you record all you have your Motec data logger armed, so that it's recording the telemetry, and then you just go very carefully through 1, 2, 3, 16 runs, and then you get it done. It's simple as that. Then the next step is to open up a spreadsheet and record all the data, and then after that, you go ahead and you create a table in Motec. by using this add 3D table or add 2D table. You gave it a name, you enter all the values, and that'll be just like how I did here. So this is Aero balance map, and I have all my values set. And then after that, you can go and have something that you can use when you're at the track, not doing straight line testing, but actually doing practice for an actual race. So let's go ahead and work through the example.